Hello all. Welcome to this video. In this video I am going to explain how to use the fast frequency sweep application that we have developed for Matlab RF PCB Toolbox. As we all know, the electromagnetic simulation is a time-consuming process when simulating complicated RF circuits over a wide bandwidth. Fast frequency technique have been developed to predict the characteristics of RF circuits over a broad frequency band of interest, based on simulations at a few sampling frequencies. In this application we have implemented the Loner matrix method for fast frequency sweep. Okay, so that was the introduction. Now let's get into the app. This application has two tabs. First tab is for frequency point generation, and the second tab is for fast frequency sweep. In the first tab, user can enter the length of the structure in meters and the minimum and maximum frequency of simulation in gigahertz. By clicking the Generate button, the application will calculate the electrical size of the structure and the input frequency points for the full wave simulation. Here please note the point that this fast frequency sweep method will work for structures with electrical size up to 3 lambda only. In the graph it will show the frequency points and the index. Now the user can save the frequency points as .csv file. Next, the user has to do the full wave simulation of the structure for the generated frequency points in Matlab RF PCB Toolbox, and has to save the S-parameter data. The second tab is for fast frequency sweep, and also in the second tab we can check whether the generated data over the entire bandwidth is correct or not by testing. For fast frequency sweep, the generated S-parameter data can be uploaded in the input file. Testing I will explain with an example. The sampling frequency is set as 10 MHz. The user can change the sampling frequency. Normally it is set as 10 MHz. The number of port will be updated automatically when we upload the input file. Now by clicking the Calculate button, the application will calculate the S-parameter data for the entire frequency band with the specified sampling frequency interval. The input and output port is set as 1 initially. User can change the port number and can plot the magnitude and phase of the S-parameter by clicking the Plot button. Finally, the user can save the S-parameter data by Save Data button. So, let's take one example. We are going to simulate a microstrip T-junction in Matlab. The total length of the structure is 25.48 mm and we have to simulate the structure for 1 to 10 GHz frequency range. We have to find out the frequency points that we need to simulate for fast frequency sweep over the entire bandwidth. For that we will use the first tab of the app. We have to enter the length of the structure in meter as 0.02548, and the minimum and maximum frequency of simulation as 1 and 10 GHz in the app. By clicking the Generate button, it will calculate the electrical size of the structure and the frequency points for full wave simulation. The frequency points and index is plotted in the graph. Total 14 frequency points are needed to simulate the structure within the frequency band. Next step is to save the frequency points as .csv file format. Here I am saving the frequency points as the name T-junction_frequency. In the next step, we have to go to Matlab and add the frequency file in the code. Here, multiply the frequency points by 10 raised to 9. Now we have to simulate the structure for the 14 frequency points generated by the app and save the S-parameter data. Here I am saving the S-parameter data as junction_input des2p. Okay, now run the simulation. After completing the simulation, we have to do the fast frequency sweep. So let's proceed to the second tab of the application, and enter the S-parameter data file we have generated after completing the full wave simulation of the 14 frequency points. When we upload the file, the number of port is automatically updated. The sample frequency is set to 10 MHz, however the user can modify it. The input and output ports are initially set to 1. By clicking the Calculate button, the application will plot the S-parameter throughout the bandwidth. User can change the input and output port number and magnitude and phase of the corresponding S-parameter by selecting the appropriate magnitude or phase option in the drop-down button by clicking the Plot button. In the graph, the red line is the generated Lohner matrix model, and the black dot is the input data we have entered through the input file. Finally, we can save the S parameter data across the entire bandwidth with the sampling frequency interval. This is the generated S2P file for the T-junction. The S parameter is generated in the 10 MHz interval, which corresponds to the sampling frequency we have specified. The S parameter is generated at frequencies ranging from 1 to 10 GHz. Okay, next we'll see if the generated S parameter data is correct or not. To accomplish this, we must return to Matlab and simulate the T-structure in the 10 MHz interval spanning the frequency range of 1 to 10 GHz. I am doing the simulation in the same code by changing the frequency. I'm saving this file as junction_test s2p. Okay, now, simulate the structure. This simulation requires 901 frequency points to be simulated, which will take time. Okay, the simulation is done, and it took 125 seconds to simulate 901 frequency points. The first simulation with 14 frequency points took around 19 seconds to complete. Okay, now we'll test, which requires us to enter the input file as well as the testing file that we generated. The application will plot the S parameter once you click the Calculate button. In the graph, the blue line represents the testing data. The graph shows that the Lohner matrix model exactly matches the testing data that we have generated in the interval of 10 MHz. The user can change the input and output port number and can plot the magnitude and phase. So, by taking 14 frequency points, our application generated the data in 1 second, resulting in a total of 20 seconds for the full wave simulation and Lohner matrix model development. Here, we saved 125 minus 20 is equal to 105 seconds. Let's do another example. We have designed a 44-port microstrip line structure and we have to simulate the structure within the interval of 1 to 8 GHz. The electrical size of the structure is 2.24 lambda at 8 GHz. We have already generated the input file and testing file. We just need to input the file. Let's do it and we'll see the result. As we are dealing with large set of data, the generation of the Lohner matrix model will take around 30 seconds here. Okay, now, the Lohner matrix model for 44-port structure is generated. Let's change the port number and plot the graph. Here we have taken only 34 points for the full wave simulation, and it took 8 minutes to complete. The generation of testing data with interval 10 MHz in the frequency range of 1 to 8 GHz took around 2 hours 20 minutes. So, here we have saved around 2 hours with our application, and we have generated accurate S parameter data. Okay, now we will save the S parameter data of the 44-port network generated. I hope everybody understood the working of our application. We have tested this app with a lot of example and it is generating accurate data. Please check with your structures and note that this app will work for structures with an electrical size up to 3 lambda only. Thank you for watching.